In the last chapter, we looked at kinematic motion in the one dimension, dealing with position, velocity, and acceleration. We talked about objects that move horizontally, and we talked about objects that are moving vertically. So just a quick summary, if we have an object that's moving horizontally, maybe this is a bowling ball that you go out bowling with your friends, you roll the ball down the alley, and because there is no friction, then that ball is going to travel at a fairly constant velocity down the alley. And you'll notice that each one of these arrows then is roughly the same length because of there being no friction involved. So the only thing affecting the ball is friction, and we don't look at that, so we would say that that velocity is always constant in the horizontal direction. Now, when we talk vertically, maybe this is you go outside and you are dropping water balloons on your friend off of a playground. So you have the water balloon. As it's falling, remember that that balloon is affected by the acceleration of gravity. And so we would say that that acceleration is the negative 9.8 meters per second squared, which means every second this velocity vector is going to get roughly 10 meters per second faster. And that's why it gets faster and faster and faster. That's why it covers more distance as we go. Now, when we talk about two-dimensional motion, we're going to combine the two of these. So I have this horizontal motion that's moving at a constant velocity to the right. I have the vertical motion that is being accelerated as we go down. And as the object goes, you think through this in terms of vectors, the object is going to have this x velocity and this y velocity. Down here, it'll have an x velocity and a y velocity, and an x velocity and a y velocity. And because of vectors, those green arrows are going to be the resultant of the path that they follow. So as the ball comes off of this ledge, it will follow this parabola and get greater and greater and greater on the y-axis because of the acceleration of gravity. So horizontal and vertical components are independent. It doesn't matter how fast the ball comes off of the ledge in the x direction. What's going to matter is how quickly the acceleration of gravity is that's pulling it down. That's what affects how fast it falls. So all of these problems are going to become two steps then. Every time we have another dimension added to that, we are going to add a step. So we're going to have a step in the y direction, but then we'll also have a second step in the x direction. And the thing that combines the two of those is going to be the time. It takes the ball the same amount of time to go from here in the x direction over to here as it does for the ball to go from here in the y direction down to here. Those two things are together. So steps for all these problems, the first thing we're going to do is break the velocity into the x and y components because we have to deal with it separately. We have an x problem and a y problem. Remember, it's y sine because x is cosine. And number two, we're going to use the x or y displacement to find time. So typically speaking, we'll use that first kinematic equation, x equals vit plus 1/2 at squared. Number three, we'll use the time to find the other displacement. So once we have the time on the other side, we can look at that in order to find the y or the x value. And then if it asks us to find maximum height, typically we'll plug that back into the squared equation, and this instead of an x will be in the y direction. And then lastly, if we need to find the final velocity, we'll put everything back together to find those values. So here's a sample problem. A plane is flying horizontally, which means that the angle is 0 at 91 meters per second or 204 miles per hour, and it drops a bag of food supplies from an altitude of 812 meters, which is roughly half of a mile. So when we look at that, what are we given? We know that the initial velocity is going to be 91 meters per second at 0 degrees. We also know that the height is going to be 812, so I'm going to call that my y, and I'm going to make it negative because I know that the food supplies land lower than they started from. Next step then. So here are our givens. We have that 91 meters per second at 0 degrees. We have our y component of negative 812. And then the one last thing that we do know is we know the acceleration in the y direction is always negative 9.8 meters per second squared. So first off, break our velocity into components. We would take 91 cosine 0 and get 91, 91 sine 0 and get 0. That's really easy in a horizontal problem. Number two, use the displacement to find the time. So which displacement do we know? We know the y displacement, which means we're going to plug in the negative 812 in for our displacement. We'll plug in our initial velocity in the y direction of 0, and we'll plug in our y acceleration of negative 9.8. So remember, everything has to be in the direction that we're talking about, which in this case is the y direction. If we solve for time then, we end up with 12.9 seconds for that. So once we have that time, we can find out how far the supplies land, so remember they're going to do something like this, we can find out, well, how far in the x direction did they land away from where the supplies were dropped. So technically speaking, this equation has a plus 1/2 at squared on the end, but in the x direction, what is the acceleration of 0? Yep, I just said that wrong. What is the acceleration in the x direction? It's 0. So if we plug in those values, then we can solve that our x velocity, 91, times the time that we just found, tells us that it will land 1.174 kilometers away from where it began. So then lastly, next to last, the maximum height in this problem is easy because the package never goes higher than it began with since it was shot horizontally or dropped horizontally. So we know automatically that the maximum height is 812 meters. Now to find the final velocity, remember that the package, when we look in the x direction, because there's no acceleration, the final x velocity is the same as the initial x velocity. But whenever we look in the y direction, that y velocity changes because of the acceleration of gravity. So as this package is falling, it's going to have an x velocity that is the same through everywhere on this. It'll have the same value, that same length, just as like the bowling ball did earlier. Whenever we look at the y velocity, so let's picture that the package lands at this point here instead of all the way down here. So here's our x velocity this way, but at this point now, it has a y velocity based on the acceleration of gravity. So I can take and plug in those values. The initial y velocity was 0, the acceleration was negative 9.8, and the time it took to get to the ground was 12.9 seconds. Plugging that in, we end up with a final velocity of 126 meters per second. So this leg of the triangle is 126. This leg of the triangle is 91. Now, how do we find the resultant of those two legs? And yep, we're going to do the Pythagorean theorem. So the Pythagorean theorem, the square root of Vfy squared plus Vfx squared gives us 155 meters per second is the velocity or the speed that it hits the ground with. Now, in order to make that a velocity, we still need a direction, right? So we're going to set our angle to be here because we want to know this entire angle here. So when I do that, my opposite value is the x value. My adjacent value is the y value. So I'm going to plug in the inverse tangent, 91 over 126, and you end up with this small angle being 35.8. So in order to get the total angle, we would have to add 270 to it, and that's where we get the 306 degrees. So our final answer then will be 155 meters per second at 306 degrees.